All right, class. So here we are with section 5.5, the Fundamental Theorem of Calculus. So to begin, I want to describe to you more or less what this is going to seem like. And so as you look at the Fundamental Theorem of Calculus, you're really looking at, and by the way, this is section 5.5. We're looking at the integral from b to a on an interval where you have f of x dx, which is equivalent to basically the antiderivative of b minus the antiderivative of a. So if I'm looking at an interval and I'm basically looking at a first quadrant, and let's say this is some value a and here's some value b, and I'm looking at the antiderivative of some function, whatever the function may be, I'm looking at the area that's sitting here between a and b, and that's what we're basically calculating for. And so for the moment, I'm going to skip example 1, believe it or not, and I'm going to actually start with example 2 because I think it'll make more, example 1 will make more sense after I go over a couple of these examples. So, and I'm also going to show you on the TI 8384 calculator how you can do this as well. So let's begin with example 2. Like I said, I will do example 1 just later after we go through some basics. So we're asked to evaluate, and they're giving us the following problem. They're asking us to evaluate this function and they're asking us to look at the values between x is 2 and x is 1 and to determine the area. So the first thing we're going to do, and think of this as step 1, is we're going to find f of b and f of a, but in order to do that, remember that that stands for the antiderivative. So we're going to take the 2x plus 3e to the x minus 4 over x, and we're going to find its antiderivative. So you know the rule. Basically, it's we're going to go with, here's a 1. We're going to start with adding 1 here and dividing 1 plus 1 here, resulting in x squared. Plus, now 3e to the x, we know that is a stubborn one. This is always 3 to the x. 3e to the x stays as such. And this, as we know it, anything over x typically will tell us that this is basically 4 times the natural log of x. Because what's 1 over x? Think about it. Okay, so this becomes minus 4 natural log x. So in essence, if I'm finding f of b, in this case b is 2, we're looking for 2 squared plus 3e to the 2 minus 4 natural log, I always do that, natural log of 2, because I am evaluating for 2, minus whatever value this gives me, minus the 1. Let me shrink it down so you see where the 1 comes from. So this becomes 1 squared, which is redundant, minus 3e to the 1 power minus 4 natural log times 1. Okay, when we do this math, we could use a regular calculator. We could use a TI 8384 calculator. In the classroom, remember, you can definitely use the technology. That's not an issue. So I'm going to model this with the calculator. So just just for a moment with a TI 8384 calculator. So let me pop this open. All right, so let's start with a basic. Let's just do this with just the numbers. So this will become, for f of b, this will become 2 raised to the second plus 3. Oh yeah, no. So 2 raised to the second plus 3 second e again to the second, and the last term is minus 4 natural log of x, which our x happens to be 2. So 4 natural log of 2, close that parentheses. Notice that we're going to get the answer right away. Lickety split 23.39, that's fine. Okay, but my recommendation is, if you don't have a regular calculator, which would require you now, for example, now you would have to do the next part, which is this minus parentheses 1 raised to the second power, which is quite redundant. This is going to be plus, again, 3 second e to the x, or e to the 1, again, quite redundant, we already know what that is, minus 4 natural log of 1. Okay, and now this is not going to give you what the value of this particular piece is. This is going to give you the entire area, which is 14.24 if you round it. But that's doing it piece by piece. Here's my suggestion. If you do get a hold of a TI 8384 calculator you can use in class or for homework, go to y equals, and if you'll notice, what I'm going to do now is I'm going to do x squared, and this is going to be plus 3e to the x, so second e, I'm just going to put in x, no smart stuff here, minus 4 natural log x again, leaving it nice and open. We don't know what's going to happen yet. After you put that in y equals, you're going to go to second graph, and you see how you have all of these values here, starting with x is 1, x is 2. Well, that's all you need for this problem. And you're basically going to subtract the 23.395 minus 9.15. Same thing, it'll land you the answer about 14.24. All right. So that's a couple of ways you can approach the same question, just talking out loud. And again, what we got on our answers for our answers, for this one we got 23.39, and this is still minus. And for this one you got 9.15, and the answer to this entire piece is 14.24 rounded. All right, let's try another question, and then we'll try one with substitution. So this is a try question for number 2. Again, remember we skipped number 1. I will go back to it. So they're asking us to evaluate. They give us the following area, 3 to 1, given 4x minus 2e to the x plus 5 over x dx. And we do the same thing. We evaluate this. So again, I remind you that this is simply, if you take the 4x minus 2e to the x plus the 5 over x, we're going to find its antiderivative. So the rule of thumb is there's a 1 sitting here. We're going to do plus 1 divide by 1 plus 1. This stays the same. This is 2e to the x will stay as 2e to the x. And remember, this is 1 over x 5 times, basically 5 times 1 over x, which we know is the same as the 5 times the natural log of x. All right, so this is what we have. We have 2x squared minus 2e to the x. That's our antiderivative function. This is our f of x function. Once again, you can evaluate this as starting with f of 3. So this is going to become 2 parentheses 3 squared minus 2e to the 3 plus 5 natural log of x. Okay, and so that's, in this case, the x would be 3, so we would just put a 3 here. If you do f of 1, in this case, you would have 2 times 1 squared minus 2e to the first power plus 5 natural log times 1. Now throwing this into a basic regular calculator, so I'm going to use the basic functions of the TI calculator. So you can do this with any calculator, FYI. So I'm going to more clear, just regular calculator. I'm going to clean this in just a little bit. So you would start with 2 times 3 raised to the second minus 2 second e to the x. In this case, this would be e to the 3 plus 5 natural log of 3. And that would land you at negative 16.67. So let's go ahead and write this down again. This is like if you had a 5-function calculator, right? All right, so I'll just write it down to 3 decimal places. And now I'm going to repeat the process. And again, I'm just modeling what it looks like in a regular calculator. Now 2 times 1 squared, we know that's 2. So I'm just going to go with 2 minus, so 2 minus 2 second e to the x, which is basically e to the 1 power. And again, plus 5 natural log of 1, close parentheses, enter. And now do a little math here. This is negative 16.678. It was 0.14, but I'm going to ignore it. Double negative, because this, remember, is b minus a. So minus, I'm going to do parentheses, and then I want the little negative integer function, 3.436563.657, and close that out. And that should not be the answer I get. So it left me at negative. We just know this becomes plus. So let's just ignore it. 3.4365. I want to say, oh goodness, I don't like mistakes. Let me go back. Negative 16.678. So minus 16.678, and it becomes plus because it's a double negative. So it's minus, and what was it that I had? 3 point something. Oh goodness. Okay, fine. We'll just tough it out. Do it this way. 2 minus 2 second e to the 1 power plus 5 natural log 1. Nice. So I'm just having to write it back in because I made a mistake. So notice you get negative 13.24, and that is correct. Okay, so in other words, the value of that missing integer was like negative 3 point something. So you can subtract it and figure it. All right, so that should be pretty easy to take in. I'm showing it to you with a calculator. If I go to y equals, I could do the same thing with just throwing it in once. So if I throw it in one time, just one time, where I had 2, this would be x. Nice. This would be 2x squared minus 2e to the x plus 5 natural log x let's see, 2 second e to the x. I just want an x. Thank you. Okay, and then plus 5 natural log x. Close it out. And that's all I need. And if I go second graph, see, there's my value. It was negative 3.43. This is 16.68. Subtract these, you'll get the same number we just got. So that's just my hint, as in if you want to save a little time, just type it in once with the TI if you're patient. Oh my goodness, if you're patient. All right, example 3. Example 3 is more of the same. The only thing we're going to do here is we're going to look at substitution techniques. Substitution techniques. All right, and so they're giving us the same direction. They want us to evaluate the following. They're giving us the interval from 5 to 0 for the function x over x squared plus 10 dx. So we need to find the antiderivative. Okay, so let's take a moment here. And understand the first thing they're doing is they're saying, let's have u for substitution be equivalent to x squared plus 10. And du be the equivalent of 2x dx. All right. So if that's the case, then that means that I have a constant here. And I'm going to write the whole way out so you can see the whole picture. So we still have x over x squared plus 10 dx. And we obtain the 1/2 from the 2x dx. That's our 1/2 function. And we're still integrating. We still have 1 over x squared plus 10 times 2x dx. So if I use u substitution now, what I have is 1/2 1 over u du, which we already know that 1 over u is natural log u, so we really have 1/2 natural log absolute value of u plus c. If we plug our u value back in, we have 1/2 natural log of x squared plus 10 plus c. And we know that x squared plus 10 as a value, the x squared plus 10 can never be negative. Technically, it's greater than 0. And so we can go ahead and evaluate the indefinite integral here. The definite integral, so we get 1/2 for natural log of x squared plus 10. and we're going to look at it between the interval 5 and 0. And so this becomes, and pay attention to this part because it's actually quite easy. We have 1/2 the natural log of 35. If you didn't catch on where the 35 comes from, let me give you a huge hint. 5 squared plus 10. That gives you 35. All right, plus, or actually minus, I forget. This is always minus, so b minus a. So 1/2 natural log 10. Obviously, if I'm putting in a 0 now, 0 squared is 0 plus 10 brings me over here. Okay. All right. So throw that into some sort of technology and you'll get your answer. This should be approximately, and we are going to round, it's 0.626. If you want to see it on the calculator, let me throw it up here. Go over here, so more clear. All right, and so we're going to do 1/2, so 0.5 natural log 35 equals minus, I'm going to put parentheses, and again 1/2, so 0.5 natural log of 10, parentheses again, 0.626, just like I said. So it's not too terrible a question, I hope. I have another try question. This one is very similar. Integrate 1 over 2x plus 4 dx. And so as we do this question, you'll end up, step by step, you'll end up with 1/2 natural log 6 minus natural log 4, which comes to approximately 0.203. So I'll let you try that one on your own, and if you have questions, you can always email me and we'll talk during class. So here we go with example 4. I have more substitution. So this is a substitution. And in this one, they're asking us to use this method where we're integrating and using u substitution. So this is what we have at the moment. So the first thing they say is, in this case, let's substitute u as 5 minus t. 5 minus t. And if we do du is equal to negative dt. Okay, so here's your t value. All right, so we begin with also the concept that if we use t equals 1, so think of the fact that t equals 1 means to us that u could also potentially just simply be 4. And the other concept is t is equal to negative 4. this actually is a negative 4, my bad. Then that means that u is actually potentially equal to 9. So if the lower limit for u is larger than the upper limit, let's be careful not to reverse these. So we have integral 1, negative 4, again, square root of 5 minus t dt, which is equal to the negative integral 1, negative 4, square root of 5 minus t, negative dt. So remember, it's always b minus a, but a seems to be a larger number. So if that's the case, then that negative integral of 4 and 9, square root of u du, you just have to follow the logic. This will actually be negative integral 4, 9 of u to the 1/2 du. Okay, so if we work this out and use the antiderivative, this becomes 3 over 2 u to the 3 over 2 over 3 over 2. Now remember, 1/2 minus 1 is, or plus 1 is where we're going with this, right? If it's plus 1, it's really plus 2 over 2. Hence, this becomes 3 over 2. That's where this is coming from. That's where this is coming from. And again, we're still evaluating this from 4 to 9. All right, and now we bring it back into the fold. So we have the negative of 2 over 3 times 4, 3 over 2, minus 2 over 3 times 9 raised to the 3 over 2. And so this becomes 16 over 3, negative of 16 over 3 minus 54 over 3, which if we reduce this would become 38 over 3. Remember, double negative, positive. And that is approximately 12.667. So that's a lot of steps and a lot of thinking, but put it all together, it's not that tough. It's really quite simple. And once again, if you want to use technology, it will make your day because, for example, let's go ahead and throw this one into the calculator. I want to see what this looks like. When you go second, let me go to Mode Clear first. Let's go with math, number 9. Okay, and let's go ahead and put in our original numbers, which was, we have a negative 4 here. So remember, it only likes the little negative integer. And this is 1. So originally, that's what our question looked like. But I'm putting in now the original question. So second, square root, we're going to do 5 minus x. It doesn't matter. I know it's a t in the question, but you can use 5 minus x. Whatever you do use, whatever it is, match it here. So if you get picky and you put in a t, isn't that our answer? Same answer. I strongly urge you, try technology first. Okay. Let's skip 5 and 6 as well. And we'll go back to it, I promise. And I want to talk to you about example 7. And I want to give you a heads up on example 7. And the reason for that is the following. They recommend, even the author of the book recommends, that you're better off at this point using technology when you have an integrand e to the x or negative x. It does not have what they call an elementary antiderivative. So we're unable to use that fundamental theorem to evaluate that definite integral. They're suggesting that we use a numerical integration routine that's programmed into the TI-83 calculator. So they literally are just saying, look, if you have a question like number 7, okay, in question number 7, this is what they give you. They give you to locate the integral between 2 and 1, negative 1 at that. And then this is going to simply be second e to the, what do they have this one at? X, negative x, and that is even the squared. So negative x and that is squared. That's what that looks like. And this is obviously dx. So what they're suggesting is when you have these types of questions, use technology. I like how that just went into quit. I don't know why that just happened, but let's see. I did use the little negative thing, didn't I? Let's try it again. It should work, because I've done it before multiple times just to test it out. What I want to change here, perhaps I hit the negative by accident. Yeah, maybe that's what it is. You notice the little negative change, so yeah, that's what it is exactly. So make sure you're using the integer negative, not the subtraction negative. So that was example 7. Let me show you what that question looked like. So question number 7. I wanted to get these out of the way so we could talk about the application questions. So they're asking you to evaluate, and then they're giving you again 2 negative 1 as the interval, and then this is e. It happens to be a negative x squared, could be a regular e to the x, it doesn't matter what it is. They're saying use technology. Even in this question, they're also saying evaluate. This is the try question. This is the one we just did in the calculator, by the way, which resulted in 1.629. They're giving us another one where we're looking at the interval from 4.3. Remember, that's the b term. The a term is 1.5. And you have x over natural log x dx. And they want us to evaluate this to about 3 decimals. Now, according to the answers, we should get 8.017. So I'll put in the math function. So math 9. And let's put this up here, 4.3. Okay, according to this question, we're going to do x, let's not do that. X divided by natural log x dx. Okay, let's see. Yep. In technology, it works. I think it's, oh my goodness, my mistake. I did not take the antiderivative. I was doing it straight up as a function. I just realized that. So yes, you would have to work this out. Find the antiderivative first, and then it'll give you, because it's coming close, but it definitely needs the antiderivative. So that would be, let's take a look at what that value should be as the antiderivative. So as stated for these two, I would definitely use the TI-83 calculator, 83 or 84. Either would work with the technology. So that is example 7. Let's look at I can go back to 1 actually at this point. I'm just going to go back in order. So in example 1, they're giving us a question. And now that you get the general idea of what is expected of this section, we can look at the question which states the change in cost versus the area under marginal cost. And you're going to see, hopefully, the connection between what we just did and a few examples and what this is talking about. And so we remember in this question, the daily cost function for a company in dollars is given by, and they tell us C of x given by the function negative 5x squared plus 210x plus 400 in the interval between 0 and 20. And they're asking us to graph the function and look at it from this particular window, 0 to 20 on the x values. Calculate, based on this, calculate the change in cost from x equals 5 to x equals 10. So to do this, quite simply, and this will be part A, I mean, we could use Desmos if you wish. So let's go ahead, let's go to the internet and I'll throw this on Desmos. Which, if you look at the numbers, they're quite drastic. So even if I pinch this in, it will take a long time. Here we are. That's about the tip of the equation. So they're asking us to look at the values where x is simply sitting between 5 and 10, which you can see is basically from here to here. We're trying to determine that interval. And if we minimized it in a calculator or in a window where we can control the window, we would see something like this, which you can understand why on Desmos it's a little hard to see. Starting with 5, 10, 15, 20. And then, as you saw, the y-axis is pretty large. 1,000 to 2,000, 3,000 is what we would end up looking at. And you saw that on Desmos. And so we're trying to get a glimpse of the values going from 5 to 10. So if you notice, let's see, at 5, at 1325, somewhere about here. And on 10, I'm at about 2,000. So at 10, I'm close to the exact 2,000. And so it's kind of doing this behavior. We're only looking at this window right here, or this little area from here to here. And we're trying to calculate the value of this trapezoid that's created here. which you'll see a little bit better in the next example because this is a curve. What you're going to notice in this case, if I do C of 10, C of 10, plugging in the values in for x, we obtain the value of 2000. And that's basically negative 5 times 10 squared plus 210 times 10 plus 400. And that's how we obtain this value. And then you do C sub 5 following the same process, which we obtained a value of 1325. Again, the equivalent of negative 5 times 5 squared plus 210 times 5 plus the 400. And so that's this value here that we're talking about. This is the 1325. So 5 comma 1325. And this value here, which is the 10 comma 2000. And so we're using those two values, and if we subtract them, if we take the 2000 and subtract the 1325, we obtain an area of about 675. And so, and this change is the cost. This is a change in cost as indicated in the first figure, in the first question type. In part B, they're asking us to graph the marginal cost. So graph the marginal cost. So in essence, we need to find that first derivative, which is easy to take. We end up with negative 10x plus 210. So that's our first derivative of x, of our cost function. Okay, and they again want us to evaluate it at 10 and at 5. So we would start with this equation at, let's see, of 10, and we get negative 10 times 10 plus 210, in essence 110, and we would take that first derivative at 5, which is negative 10 times 5 plus 210. Oops. And then we end up in this case with 160. And in the area formula for a trapezoid, we do area is equal to the top value of 160 plus 110, the bottom value, divided by 2, so the average of them, and then times 5, which is basically the 10 times the 5. And we end up with, again, 675. So there's no difference, which answers part C. Part C wants us to compare the results. So this is just proving that regardless of which of the two methods, we are still going to get the same answer. So once again, that goes back to the fundamental theorem that I discussed earlier, where we have an integrand, we have an interval, AB, but we always subtract, if you think of the function, we have f of x dx, which once we take the antiderivative, we're going to subtract the value with b as substitution and the value of a, so b minus a, and that gives us that area under the curve that we're looking for. So we already did examples 2 and 3. I believe we did example 4. Example 5 is a change in profit question, which we have not done. So let's look at example 5. They give us a change in profit question, And the question reads, basically, a company manufactures X HD TVs per month. The monthly marginal profit is given by, so this is the monthly marginal profit is given as P, first derivative X, equal to 165 minus 0.1x between the interval where X is between 0 and 4,000. It then says the company is currently manufacturing 1,500. So they're manufacturing 1,500 TVs per month. But it is planning to increase production. They want to find the rate of change. So the question stem is basically find the change in the monthly profit find the change in the monthly profit if monthly production is increased to 1,600 a month in terms of how many they're going to produce. So given this information, we need to find the original P at 1,600 and take away the value at 1,500. So comparing the two production rates, which as an integral looks like this. You have the 1,600 is your B term, the 1,500 is your A term, and you're given the function 165 minus 0.1x dx. So that's how this integration concept ties in with an application question. We're looking for some sort of change. Now, the first thing we're going to do is we're going to find the antiderivative. So once we find the antiderivative, which in this case would become 165x minus 0.05x squared, because remember you divide by the exponent as well. And we're going to find this between 1,600 TVs produced, 1,500 TVs produced. So if we apply the formula, we would end up with 165 times 1,600 minus 0.05 times 1,600 squared. And we're going to take this and subtract from it 165 1,500 times 1,500 minus 0.05 times 1,500 squared. And let's take a moment and just do a little calculation. We find that this gives us 136,000. This gives us 135,000. And the difference between these two values obviously is 1,000. So how we would interpret that is basically increasing the monthly production that is awful. Let me rewrite that word. Monthly production from $1,500 to $1,600 would increase the monthly profit $1,000. In the grand scheme of things, it would be up to the company to determine that. Okay. The other example would be example 6. That's another application question I'd like to share with you. This has to do with useful life. So it talks about an amusement company maintains a record for each video game installed in an arcade. Suppose that C of t and R of t represent the total accumulated cost and revenue in thousands of dollars respectively, t years after the game is installed. It says the first derivative of t is equal to 2, and the second derivative of t is equal to 9e to negative 0.5t. The value of t for c, the first derivative of t, and r, first derivative of r, is called the useful life. Useful life. So again, that's relating to the C of t and the R of t. It says find the useful life in the game to the nearest dollar. So the first thing we would do is in part A, we would set R of t, our first derivative of t, equal to the first derivative of c. So in this case, we would have 9e to the negative 0.05t is equal to 2. And so first things first, we would obviously divide by 9. So if I divide by 9, step 1, I end up with e raised to the negative 0.05t is equal to 2/9. I'm then going to take and divide by e on both sides, which once I do this, I'm basically taking negative 0.05t on the left hand side and setting it equal to the natural log of 2/9. Okay. In doing so, my next step would be to divide by negative 0.05 on both sides, leaving me t is equal to negative 2 natural log of 2/9, which if you do it in the calculator, if you notice, is very calculator intensive unit, because there's no one knows their natural logs by heart. So it says the game has a useful life of 3 years based on this formula. All right. Find the total profit accumulated during the useful life of the game. So they're asking us in part B to take P of 3 years minus the initial time. Again, this basically is an integral, taking that first derivative, and that's how you set it up. That's the connection. They want to know, in this case, the profit. So we begin with, again, our notation, and we know that we're looking at 3 years' time. And we set it up with what we do know, which obviously we already know that this is 9e to the negative 0.05t minus 2, and that's given to us in the equation. If we re-express this, and you need to go back and recall something, recall that if you look at this, the 9e to the negative 0.05, this is the equivalent of a to the x dx, which reduces or is equivalent to 1 over e to the ax plus c. And that's one of those fundamental theorem or concepts. So we can re-express this as 9 over negative 0.05 e to the negative 0.05 t minus 2t in the interval that we're looking at, which is our interval from 3 to 0 years. So if we reverse the math here with the negative 0.05, we end up with negative 18 e to the negative 0.05 t. I keep saying 0.05 and I just realized that it's actually 0.5. My apologies, I don't know why I did that. So 0.5. I hope you ignored me as I was doing it. Minus 2t, again, same range from 3 to 0. And reducing this, we end up with, if I substitute in the value, I'll end up with a negative 18 e to the negative 1.5 minus 6, basically substituting in the 3, minus, and now we're substituting in the 0, you get minus 18e to the 0 minus 0. This simplifies further. You end up with 12 minus 18e to the negative 1.5. And throwing this into the calculator, somewhere approximately 7.984 is what you should get, which represents approximately $7,984 that you should profit from for 3 years using the game. All right. I think I made the same mistake up here and I didn't catch it because I wasn't calculating it, or did I? I think I did. All right, I think we're okay. No, we're not okay. I did the same thing up here, and for some reason, since I wasn't calculating it, I was just discussing it with you. I put the 0, and there should not be a 0 here. That's all. We divide this, and when I put it in the calculator, interestingly enough, I actually did put in 0.5, not 0.5. Go figure. So, okay, so just remember 0.5, little mistake there. All right, we did example 7. We could talk about the average value of a function, which is example 8. This is the average value of a function. And so in this question it says find, and pay attention to this one because this is a very common question. Find the average value of the function f of x is equal to x minus 3x squared over the interval and they give you the interval where you have -1, 2. And so to find this answer, we're going to use the average value of a continuous function over the interval AB, which is simply 1 divided by b minus a times the integral where you have b to a of f of x dx. Okay, so this would be your average value function right here. This is what you'll follow as a trend. So let's go ahead and let's calculate this one. So to set it up, they give us a function. We know the function already. So this will be basically 1 over, so I'm following this function, 1 over 2 minus -1. And this is over the integrand times the integrand to -1, where you have x minus 3x squared dx. Okay, so we begin with some basics. We're going to add 1. Remember, this is to the first power, this is the second power, so we're going to add 1 to each of these and then divide. So 1 plus 1, and this becomes 2 plus 1. So you can see where we're getting 1/3. This becomes x squared over 2 minus x cubed. And we're still evaluating in the area from 2 to -1. A little distribution and substitution, you're going to end up with -5 over 2. So that's pretty basic math after that. You end up with a figure that is running like this. If this is the x-axis, and you have y interval -1, -2, -3, this is somehow floating in the area where y equals -5 over 2. So this is y equals -5 over 2. And if you were to graph this function, it is cutting through these two numbers right here. So it's going through here, something like this, where this is the diagram for f of x equal to x minus 3x squared. You can graph that in Desmos and see it much more clearly. Let me go ahead and do that. So let's go to Desmos. This one actually will see, you will see clearly. So you have f of x is equal to x minus 3x squared, right? So that's your function. And here comes y equal to -5 over 2. And you can see the diagram right there. Those are your cutting points. So that's pretty easy to understand, I would think. Though that's where we would find the average value of the function, which is the y equals -2.5, basically. All right, question number 9, which is our last example. In this question, we have example 9. This is an average price question. So this says they're giving you a demand function. I'm just going to put f of x, you get the idea. They're saying the demand function for p is d of x is equal to 100e to the -0 point. Let me make sure that's a 0.5 for sure. It is. All right, and they want to find the average price over the demand interval and they're giving you the demand interval from 40 to 60. So following the notes I gave you earlier, we would do 1 over b minus a. And then here's your interval from b to a. And then we're doing the d of x dx. In our example, we're doing 1 over 60 minus 40. So that's our interval. And we would write 60 to 40, given the value of 100e to the negative 0.05x dx. And so little math, you end up in this case with 100 over 20. And again, just remember, e to the ax dx becomes the equivalent of 1 over a to the x, where a is obviously not 0. So 100 over 20, here's your integral. Obviously you know where the 20 comes from, the 100 obviously from the transformation of the function. So you end up with you understand when I say the transformation of the function, I'm referring to the 100. Notice that there's no 100 here anymore, just in case I'm skipping steps. So 0.05x dx. All right, and so we reduce this a little bit. 5 goes into 100, 20 goes into 105 times. So you end up with negative 5 over 0.05 e to the negative 0.05x. Again, the interval of still 60 to 40, which reduces to, remember now we have 100 times e to the negative 2 minus e to the negative 3. And the value for that is approximately, you got to throw it in the calculator, you do get 8.55. So it's approximately $8.55. And so that is a general idea. Now I want you to note this, and this is my final say, as I know I've been at this for a while. There are some questions that are in this section I will not throw you in your direction, like anything involving natural base e or natural log x. I will not give you those questions on the test. I'll just show them to you here. Only reason is because if you're in class taking a test, you don't have the technology, it's not a fair system. So I'm not going to do that to you, okay? But I am going to give you questions you can derive yourself, do the antiderivative without issue.